Hey everyone, in this lesson we are looking at what's called the universal wave equation. Sounds pretty important, right? So the universal wave equation is really an equation that gives the speed or the velocity more specifically. If you know the direction, I'll talk about that soon and more later on as well. Um, so it gives the speed or velocity of any wave. It's called the universal wave equation. All right, and so the difference between speed and velocity is with speed, you're just talking about the value only. It's just the speed value, and that's called a scalar. I'll circle that in a second. Whereas with velocity, they you put a little arrow over top of it, or even just a bar, and so you have a direction also. So 50 kilometers per hour north, for example. All right. So this one right here, right, it's called a vector quantity. It just means that it has a direction also. Okay. Ooh, just squeezed it in there. So it has a direction also. And what color do I want to do? Let's do a different color here. Orange or something. Speed here, right? That is a scalar. Okay, so it's just the value. There's no direction. Okay, so scalars versus vectors, kind of, sometimes people do like an official lesson on that, but basically it's just a thing to know, so it's not that big a deal. Okay. So if we're looking for speed for waves, speed equation for waves, let's look at the concept of speed itself. Pretty familiar. You see it along the side of the highway all the time. The speed limit signs here, and you've got kilometers, which is a distance, and you've got hours, which is a time, right? And so if you think about that, you're talking about how many kilometers per hour you're going. So really, kilometers per hour is a distance divided by time. It's distance per time, kilometers per hour. And so the equation that goes along with it is perfectly matches the concept that we know and understand. Okay, so the only thing we're kind of adding to this now is we're saying, okay, well, what about for waves, right? What would those quantities be for waves? Well, obviously, speed will just be the v, or the v with a vector if we know the direction. So let's add this in. Let's say arrow here, right? Vector if the direction is known. A little bit too big of a deal is made of this, I think, but we'll see later on when we talk about it in the motion unit. So for waves, what's the distance a wave goes that we know, and the time interval that happens in? Well, there's really your wavelength and your period, right? So the distance, the length of a wave is the wavelength, and the time that takes, or takes the frequency of the vibration to create that pattern is the period. Okay, so you've got the wavelength and the period. So let's jot that in just for. Right, so it's the period of the vibration. Maybe I should add that in. So the wavelength of the wave and the period of the vibration. Yeah, it's probably enough. All right, so we have that as a main starting point, at least. But that leaves us with this speed equation being wavelength over period. And yeah, people just tend to not like working with fractions as much. So scientists look at that and say, okay, well, we can modify this, right? So period, what do we know period is from a previous lesson? Well, we know that frequency equals 1 over period, period equals 1 over frequency. They're reciprocals of each other, right? So frequency equals 1 over period, or period equals 1 over frequency. We know they're reciprocals. And so that becomes this. And then we look mathematically at that and say, well, how do we divide by a fraction? That's the trick where you invert and multiply. Okay. Anybody wants an explanation as to why that works, I certainly can justify that as well. But it's a physics class, not a math class. So let me know if you want help with that. But that's just the mathematical equivalent of dividing by a fraction. And so we end up with the tops multiplying with the tops, and the understood one in the bottom here multiplying with the the one in the bottom there. And that was sort of there because we did the reciprocal. And so we have really wavelength times frequency. And so people just tend to call it V equals F lambda. It's just the traditional order of the way it's listed. It's just V equals F lambda. That's your universal wave equation. Okay, so that gives you the speed based on the frequency and the wavelength of any wave. Doesn't matter if it's water waves, waves in a spring, earthquake waves, electromagnetic waves of light, all the different versions of light, and so on. Okay, it describes any kind of wave. So let's look at working with this equation. And I have a unit conversion in here, so I'll mention other unit conversions as well. I suppose I'll have to do that centimeter one right away, but we'll get to the other ones in a second, I guess. So let's do this. We're going to say, okay, well, what's our, as always here, what's our given information? And so we have the frequency of the vibration listed as 3 hertz. Right? So when you read this, at 3 hertz, right away you're saying, okay, there's my frequency. Not a bad idea to circle and do this, right? To help yourself keep track of what you know and where to put it and so on. So wavelength is the 50 centimeters. And right away there, you should be saying to yourself, okay, really preference here is to go to SI units. So basically, I should say, let's switch it to SI units. And so that would be, right, need to switch to meters, right? So centimeters to meters. You have 1 meter is 100 centimeters. And so if we have 50 centimeters, using ratio is pretty easy to see that you would need to divide by 100 to make that happen. And so we're going to divide by 100 here. Make that happen, right? So we end up with this answer of dividing by 100, of course, moves the decimal place twice. It's too easy to even really talk about maybe, but there you go. You got your 0.5 meters. Okay, so you list this as 0.5 meters. There will be some questions where it'd be tempting to just work with the given units. For example, if it's given as kilometers per hour and the time is given as hours, and you can just go ahead and work with kilometers per hour and hours and get the number of kilometers, let's say, that the thing traveled. And then after that, maybe switch it to meters so that it meshes well with other units. But you can't ever have units that are mixed. In one part of the concept, you're working kilometer or distances in kilometers. In another part, it was in meters. You're obviously going to be off by a factor of 1,000 in that case, right? So that wouldn't be any good. Okay, so converting units, very important. Other unit conversions, we have your 1 kilometer is 1,000 meters. We have 1 hour. So we got minutes and seconds. Let's do the minutes. One minute is 60 seconds. If we go for 1 hour, we'd kind of have to multiply by 60 to get the number of minutes, and then multiply by 60 again, right? So you're gonna have like 3,600. And kilometers per hour to meters per second. So 1 kilometer per hour is actually 1 meter per second is actually 3.6 kilometers per hour. I remember it as meters per second is kind of unfamiliar, and meters per second is kind of like faster than you'd think maybe. It's like almost 4, it's almost 4 times what the number would mean in kilometers per hour. This one we'll see later on. We'll see why later on. And so I'd kind of rather you not use that one as much because we don't really haven't looked at it fully yet, and I don't want to do it right now. I'll do it in the motion unit later on when we're dealing with that a little bit in more detail. And so finally here, the question was, what's the speed? And so that's your V question mark, right, that we're looking for. And so when we look at this, where do I want to do this here? Maybe I'll go like this. right? So when we look at that, we're like, oh, I know an equation to that. V equals F lambda. And so we can start plugging our numbers in. So we have our V. This one's set up nicely to just be an evaluate situation, not a solve situation. So your 3 times your 0.5, and you get half of 3 is 1.5. So you have 1.5 meters per second is the speed of the wave. So therefore, blah, 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 1.5 meters per second. The speed of the wave is 1.5 meters per second is the idea. Okay. So this is what your solution should look like. You should start with the equation with the variables, numbers plugged in, mathematical process for solving, the givens listed. This is what things need to look like. I've had some people submitting a page with just answers, and then there's a second page with just a bunch of like rough work that's super hard to follow. Not acceptable, unfortunately. Okay, so you need to have this modeling the kind of solution and the way it should look. So work towards that, please. Now, the other thing I'll show on here, maybe we'll do it in purple, is that idea of number of decimal places. So number of decimal places to keep here, basically. So that's what we're going to call significant digits soon. But I like doing it like this, where I just talk very logically about how many decimals it makes sense to keep. Then when we actually do the not so exciting significant digit lesson, it kind of makes a lot more sense to us. We understand why it's important. Okay. So it all depends on what level of precision was known in the stuff that you were given, right? So if this was actually 3.00, for example, textbooks, the textbook resource we're using, this one here, it's on the, I already showed you in the previous video, I think, that it's on the school site or our class site or whatever in D2L. It says somewhere at the beginning of it that all numbers are to 3 significant digits, unless otherwise stated, basically. So 3 is actually 3.00, or they might have listed it like that in the question in the textbook. They tend to, and people may wonder, like, why are they showing all those zeros? It's just showing that that's how accurate they're saying the frequency was measured. With the 50, technically then that would have been like 50.0 if it was always 3, right? Otherwise, it's a little bit unclear here. We'll talk about later on why that is. But you might think of that as like either 1 decimal, or it might be 3 decimals of accuracy. So it's not just a half a meter; it's like a half measured very precisely down to like the nearest centimeter or millimeter. Okay. So if that's the case, then you would keep the same sort of amount in the end. And in this case, it's a little bit hard to see like why that might matter. Like it'd be like 1.50 meters per second. But think about the case where if it was really just approximately, so that would make sense, right? The purple version. If we went with, say, an orange, or let's go orange version of things. So, or if it was literally just 3 hertz approximately, right? If it was 3 hertz approximately, and this was really just like around 50 centimeters, like literally just the 1 digit, then really it would only make sense to keep 1 digit in the end. You can't really trust that 5 anymore, right? You could trust the 5 for sure if it was actually 3 significant digits. But here you could say like, well, the 5 is, give or take a fair bit, right? Because of the lack of accuracy or precision in the first, in the given numbers. So in which case, then you'd be rounding this thing, to 1 decimal place, right? So if it's only 1 significant digit, so I'll add onto this significant digits or SDs, right? Just for short, you'll see some short forms in this course for sure. So if this was just 1 significant digit, then really you'd round this thing to V equals 2 meters per second. And the idea is just you don't want to keep a ton more information in your answer and have people think that it actually is reliable, because then they might trust it and it might matter, right? It might make the project fail, or people might get hurt or whatever. If you're building something and it's like, okay, this will be safe as long as I can count on this measurement, you need to be able to communicate that in science. Okay, so I'll keep mentioning this kind of thing once in a while, and then when we have the official lesson, um, generically for the course, I always want you to sort of at least round reasonably, right? If you do a 1 ÷ 3 as your work, and then you're like, oh, okay, so the distance, or let's say the wavelength ended up being 0.33333, and you list this as your answer, you better believe you're going to have some kind of mark deduction and a comment made saying like, okay, obviously, are you trusting all of these really, right? So if you had your wavelength was 1/3 because of the numbers being 1 and 3 for the frequency and V equals F lambda, frequency and wavelength, no, V equals F lambda, the speed and the frequency, if they're 1 and 3, then, obviously you'd need to round reasonably and say, oh, okay, so it could be like 0.3, or it could be, 0.33, or 0, you're just going to round reasonably. As long as you're doing that generically in the course, you're not going to see mark deductions. There will be once in a while a question where I will say, in this question, make sure to be very obvious and deliberate about the number of significant digits you keep. And that'll happen after, of course, the official significant digits lesson, right? All right, so keeping going here, in part B of this, it says how long will it take to travel 4 meters? I have this one just ready to go. You have to sort of switch gears and not use the V equals F lambda equation anymore. Instead, you're just using a generic speed, distance, and time equation. So there's that delta that we talked about previous lesson, where we talked about the change in, so the change in position and the change in time, right? And so it's saying like, how long will it take to go 4 meters? And so my given information is, okay, there was a 4 meters we're looking for. We're wondering how long that'll take. And we know the speed from the previous result. And so you just plug numbers in and solve, right? So the number goes in for speed, the number goes in for distance, multiply both sides by delta t, divide both sides by 1.5. This is how you need to show things, okay? This is how it needs to be done. So the units for this is in purple here is a unit analysis, right? If you're looking at how your units jive, if you didn't have both of these things, thinking of it in terms of meters, then these wouldn't cancel out, right? If you look at meters and meters canceling out here, that wouldn't work out if this was actually kilometers and this was meters or something. You're going to be off by a factor of 1,000, and that's not so good. Yeah, so your time is 2.67 seconds for this to happen. If, let's just say, if this was 4.0 and this is 1.5, then we'd be needing to round, right? If it was only 2 significant digits, then we'd say, oh, this is actually 2.7 seconds. So what you do is you keep lots of decimals all the way to the end, and then you just round appropriately at the end. Okay, so this was if it was 2 significant digits, right? So 2 SDs. And there's basically, I'm showing you what we can do just naturally. There are some specifics we covered later on to do with it, but it's not a great way to start a course. So it's not a super exciting lesson, right? So I'll come back to it later once we have more experience with it and understand why it's necessary, why it's important. All right, so we have, if a wave with a wavelength of 2 meters travels 100 meters in 5 seconds, find or determine the frequency of the vibration that caused the wave. So this is just a very straightforward one as well. Notice there's no problem units here. You've got your SI units are all matched up nicely. So I'm just going to show this one where you would have said, okay, you're given, obviously you could pause and try this thing. That'd be a great active way to learn. And then, follow along with what I show right afterwards. So feel free to pause and try this and so on. You should be able to do this at this point. Okay. So hopefully that worked out for you. You've got your wavelength was listed as the 2 meters, your distance it travels in 5 seconds. And so the difference actually, this one's a little bit of a challenge where it's the first one maybe you've seen where there's like a 2-part question, right? And so in this one here, you have to sort of notice that the distance and time, you can actually, you need to actually use the basic speed equation first to get the speed. Then you have the speed as a new variable in here, right? So basically here we have to say first, right? We're going to do this one. And then you have like a new list of information. You got your V equals 20 meters per second. or 20.0 if you're listing specifically your number of decimals that you trust, right? So then after that, you're like, oh, okay, so now I've got my frequency I'm looking for, my V, and my wavelength, right? So then you can go, right? So then you can go and do V equals F lambda and get your number. Okay, so in this case, numbers went in, you had to divide both sides by 2. Okay? If you did a unit analysis here, you'd notice you have speed, which is meters per second, divided by wavelength, which is meters. And so the meters cancel out. You're left with 1 over seconds. 1 over seconds as a unit, right, is exactly this. It's hertz. Okay. So hopefully that's making sense. Yeah. All right. So a neat application of this. What did we learn in the past about the frequency of a wave once it's created? Think back. It's made by a vibration. That's in the past. That doesn't change, right? And so we learned that this frequency never changes. Now, the weird thing is, some weird things happen when you're watching waves and that the speed of a wave can change as it goes into different materials, because it depends on the material based on yesterday's lesson. We found that if we had a dense spring versus a light spring, or the less dense spring or whatever, the speeds change, or if the tension, if something changes. And so if the speed of a wave decreases as it goes into a new material, you might see something like this. Right? So this wavelength here, right, from all the way from there to there, it goes into a slower material, that wavelength, right? The wavelength is going to decrease. You could think of that very naturally as, I'll show here, if I had wave fronts going along. In a certain amount of time, they travel this far, right? When I get into the new material, let's put a boundary here. We have wavelength going on, and then, at this point here, now it's the slow material. This is the fast speed of the wave, is fast in it. When we get to that point, instead of the wave traveling this far, it's only going to travel, half of that or a quarter of that or whatever, right? If it travels a lot less distance, obviously the wave fronts, so the parts of the wave are going to get squished together. Okay, so the wavelength decreases. Okay, so that's just very logical. If we're looking at the equation, so if we had V equals F lambda, mathematically, the wavelength kind of has to get smaller, right? Because if the speed decreases, then and this number has to stay the same. So this one has to stay the same. The frequency is still just whatever value. If we have, let's move this out of the way here. We have to have like a smaller number multiplying onto an equal value. So picture this. This was, say, a speed of 6 equals a frequency of 2 times 3, right? Well, if that speed ends up half of what it was, it's only 3 now. Well, some kind of number has to multiply onto 2 to give you 3, right? So you'd be like, some kind of number multiplies onto 2 to give you 3. If you make an equation, that's pretty easy to work out, where you're like, oh, okay, so that'd be 2. The unknown we'd solve for by dividing out to 2, right? It would give you 3 halves. So you picture how this thing is, smaller now. It's only 3 halves instead of 3. It's 1.5 instead of, right? Which makes sense, right? So this number here would be the 1.5. Okay, it decreases. So it's good to be able to think about the equation itself as well as the logic, right? So logic of it happening, and then how that looks in the equation, kind of the level you want to get to, right? So because this one stays the same, if this one gets smaller, then this one would have to get smaller as well in order for it to still be equal, right? So we've established the logic of this. The part we're missing here that actually happens in real life is, what about the energy of a wave, okay? And so the energy of a wave, I'll just tell you right now, but basically the energy of the wave is sort of represented in this here. It's the amount of water, right? So the amount of water that's kind of lifted above the rest position. So think of it as the amount of water, lifted, and just in particular lifted above like that rest position that the water is normally at. That's kind of the amount of energy, right? And so if you look at this new picture they have, there's something not right, right? The amount of energy isn't right there. And so you have really more surface area you need, right? You need kind of this much surface area to be the same as it was. And so the wave actually grows. It actually goes taller and taller as a result. Okay. And then if you think about, water isn't very stable when it goes taller and taller, right? And so it actually falls over. And that's exactly why, like, that's the physics of why waves crest and fall over as they do. Because it turns out that down here, shallower water is a slower wave speed. And that literally causes this waves falling over, which I just think is pretty cool, right? It causes that to fall over. So now you kind of understand something a little bit more about the world around you that you've seen lots of times and maybe didn't give any thought. But to see that it's linked to the stuff we're talking about that seems pretty abstract, waves on springs and sound waves and so on. It's a big connection. Okay, so the application of this, explain why waves crash the beach the way they do. So be able to explain that kind of thing, right? As I did here. So we probably should watch the waves here in the dude getting destroyed. So that's just what it was called on YouTube when I found it. I'm just gonna search my videos for dude. Probably aren't any other ones called that. So there are a couple. Dude gets destroyed. Dude does a 360 flip. All right, we're gonna have to watch the other dudes later on. So here we go. Dude gets destroyed by a huge wave.
Take it, Reggie.
Oh my god.
And watch how tall that wave gets. The wave out here is just, doesn't look that bad, right? But when it gets into a region where the speed, so there's the wave coming in, right? It's not that huge. But then as it gets to a point where the speed decreases, then the wavelength decreases as well. And all that water has to sort of pile up. And so the energy of that wave all just comes crashing down. Isn't neat. There's a really big one. Like that one.
It's dead.
So you can really see that that energy like this just piling up on top, or in this one too, right? And then it falls over. Now in some less extreme cases, you can still see it, right? But just watch next time you see waves coming in, especially if it's nice. They're fairly separate waves. I don't want to say a calm day if you have to have waves still, right? But you can see that. It's not as obvious, but I think you'll be able to pick it out next time you're beside a lake seeing waves and they're going into a shallow area. You can even navigate based on that. Like the waves will behave differently in an area where it's only like a foot deep and you can't see the rocks, right? But the waves will behave differently than they do in an area where it's 20 or 30 or 40 feet deep. Right? So as a boater myself, I watch for that. Watch for the different patterns in the waves that indicates what's underneath because of the change in the speed and change in the wavelength and conservation of energy, really. So later on when we talk about conservation of energy, I could refer back to this, be like, conservation of energy is why this happens along with the other details. Okay. All right, so the question sheet here, the first set of questions are really just about what we did in this area here about like why the equation makes sense. These equations in the middle are basic, the main practice questions. There's one here with unit conversions. This one here has sort of unit conversions to deal with. Some of them don't, and so on. So watch that. Remember, hertz is per second. So in this question, you got meters and seconds. So it's all set up for you. It's already the nice units. This one has a centimeters. So you're going to convert that to meters, right? Always have proper units as a mix so that they blend together properly. So that's the main stuff. And then there's just optional extra practice questions here for you on top of the 13A and 22 are about the changes. So like what would happen to the wavelength if the period of a wave is doubled? What would happen to frequency if the speed changes and so on? Okay, so just be able to answer those and ask for help if you need it and submit them when you're done. All right, so that is it for that for now. See you next time or whatever. whatever. Okay, thanks for watching. I won't see you, I guess, because it's just a video. Anyways, thanks for watching.